Water itself covers about 71% of Earth's surface, and that single fact explains why our planet looks so blue from space, why coastlines shape so many climates, and why the ocean's slow, steady behavior can influence weather patterns far inland. The oceans hold about 96.5% of all the water on Earth, which means almost everything watery we experience. Rain, rivers, lakes, even the moisture in the air comes from a much larger saltwater reservoir that constantly exchanges heat, gases, and water vapor with the atmosphere. Only a small fraction of Earth's water is fresh, and much of that fresh water is locked away in ice and stored underground, so the rivers and lakes that people see every day represent just a thin, active surface layer of the planet's total water. Rivers and lakes together contain only a tiny share of Earth's total water compared with oceans, ice, and groundwater, which is why protecting and managing these visible waters matters so much. They can be small in volume, yet huge in importance for ecosystems and human life. The deepest known point in the ocean is Challenger Deep in the Mariana Trench, reaching roughly 10.9 to 11.0 kilometers down, a place where the darkness is total, the pressure is crushing, and yet water still exists as a liquid environment that can support specialized deep-sea life. Ocean pressure increases quickly with depth, and by the time you reach the deepest trenches, the weight of the water above creates pressures so intense that they change how gases dissolve, how materials behave, and how organisms must be built to survive. Water can remain liquid under very high pressure in ways that feel surprising compared with everyday experience at the surface, because pressure changes the conditions where different phases, solid, liquid, gas, are stable. Typical open ocean seawater has an average salinity around 34.5 to 35 psu, meaning it carries a steady background of dissolved salts that shape density, freezing behavior, and how heat and sound move through the sea. Because dissolved salts lower the freezing point, typical seawater freezes near about -1.9 TRAS rather than 0 TRAS, which helps explain why oceans can stay liquid in extremely cold polar air while still forming sea ice at the surface. When sea ice forms, much of the salt is pushed out of the ice and left behind in very salty brine, and that brine can sink, helping create dense water masses that contribute to deep ocean circulation. The term thermohaline circulation describes large-scale ocean movement, driven by differences in temperature and salinity. A slow global conveyor that helps distribute heat and influences long-term climate patterns. The ocean acts like a vast heat reservoir because water stores heat efficiently, so the sea can absorb energy when the atmosphere warms and release it slowly later, smoothing temperature swings over seasons. Much of the excess heat added to Earth's climate system is absorbed by the oceans rather than the atmosphere, which means ocean warming is a major part of how the planet responds to changes in greenhouse gases. Hydrothermal vents release hot, mineral-rich water from the sea floor, and around them entire communities can thrive without sunlight, powered instead by chemical energy from Earth's interior. At hydrothermal vents, superheated fluids mix with cold seawater, and minerals can precipitate instantly, building towering chimney-like structures that grow, crumble, and rebuild over time like underwater geology in fast motion. Some deep-sea ecosystems rely on chemosynthesis rather than sunlight, using chemicals such as hydrogen sulfide as an energy source, showing that water can host food webs that run on chemistry instead of photosynthesis. Brine pools are patches of extremely salty water on the seafloor that can be so dense they form lakes underwater, creating sharp boundaries where normal seawater floats above a heavier, saltier layer. Waves carry energy across the surface while water itself mostly moves in looping paths. So a wave can travel long distances even though individual water parcels tend to rise and fall rather than moving forward with the wave. Tsunamis are long wavelength waves usually triggered by sudden seafloor movement, not by wind, and their long wavelengths let them cross entire ocean basins with little loss of energy until they reach shallow coasts. Tides are driven mainly by the moon's gravity, with the sun adding a smaller effect, and this steady pull creates rhythmic rises and falls that reshape shorelines, mix estuaries, and influence coastal ecosystems. Water is a polar molecule with an uneven distribution of electrical charge, and that polarity is a quiet superpower. It helps water interact strongly with many substances, dissolve salts, and form the molecular attractions that make liquid water behave the way it does. Hydrogen bonds between water molecules are individually weaker than covalent bonds, but they occur in huge numbers, and together they create many of water's special traits, like strong surface tension, high heat capacity, and a tendency to cling to itself. Water's high specific heat means it takes a lot of energy to warm it up and a lot of energy to cool it down, which is why oceans and large lakes act like thermal buffers that keep nearby climates more moderate. Water's high heat of vaporization means evaporation carries away a large amount of heat, which is why sweating can cool the body effectively, and why evaporation from oceans can transport energy into the atmosphere. Ice is less dense than liquid water at typical temperatures, so it floats, and that floating ice forms an insulating cap on lakes and seas that can protect the liquid water underneath from rapid heat loss. Water reaches its maximum density at about 4 densely, which creates a fascinating seasonal pattern in many lakes. Water can sink as it cools toward 4 densely, but once it gets colder than that, it becomes lighter again and stays near the top. Because the atmosphere holds only a limited amount of water at any moment, humidity can change quickly with weather systems, and small shifts in temperature can strongly affect how much water vapor air can contain. The water cycle moves water through evaporation, condensation, precipitation, runoff, infiltration, and transpiration, and it works like a planetary recycling system that continually reshapes landscapes and supplies ecosystems. Oceans provide a major share of atmospheric water vapor through evaporation, so even rainfall far inland can begin with ocean water that evaporated, traveled as invisible vapor, and later condensed into clouds. Most precipitation falls back into the oceans, while a smaller portion falls on land and feeds rivers and groundwater, and that imbalance explains why land freshwater is so dependent on constant cycling and renewal. Snowpack stores water seasonally, holding winter precipitation as ice and releasing it later as meltwater, which is why many regions depend on spring and summer snowmelt to refill rivers and reservoirs. Glaciers store fresh water for long periods, and their melt can sustain river flow during dry seasons, acting like slow-release water towers, though their long-term shrinkage can reduce that steady contribution. Groundwater is water stored in the pores and fractures of soil and rock, and it often represents a hidden but essential supply that can feed springs, support wells, and keep rivers flowing during dry periods. An aquifer is a geologic formation that can store and transmit usable groundwater, and the way it's made, sand, gravel, fractured rock, or porous layers, determines how easily water can move through it. Recharge happens when water infiltrates the ground and percolates downward to replenish groundwater, and the rate of recharge depends on soil type, vegetation, land use, and how intense or gentle rainfall is. The water table marks the upper boundary of saturated ground, and it can rise after wet seasons and fall during droughts or heavy pumping, quietly tracking the balance between recharge and withdrawal. In coastal regions, overpumping freshwater aquifers can allow seawater intrusion, where salty water moves into freshwater zones, making wells more saline and often harder to use without treatment. Rivers carve landscapes through erosion, transport sediment downstream, and deposit it where flow slows, meaning flowing water is both a sculptor and a builder, reshaping valleys, plains, and coastlines over time. Deltas form where rivers deposit sediment at their mouths, and their fertile soils can support dense ecosystems and agriculture, though deltas also shift and sink naturally and can be sensitive to changes in sediment supply. Wetlands can filter water by slowing it down, trapping sediment, and processing nutrients through plants and microbes, so they often improve water quality while also providing habitat and flood storage. Floodplains can reduce flood peaks by giving rivers room to spread out and temporarily store water, turning extreme flow into a wider, slower sheet that lowers downstream risk. Drinking water treatment often uses multiple barriers, removing particles, filtering and disinfecting, because no single step is perfect, and layered protection makes it much harder for pathogens to reach consumers. Disinfection commonly uses chlorine, ultraviolet light, or ozone to inactivate microbes, and each method has a different strength. Chlorine can leave a lasting residual, UV acts quickly without adding chemicals, and ozone is a powerful oxidant. Wastewater treatment typically separates solids, breaks down organic matter using microbes, and disinfects before discharge or reuse, helping protect rivers and coasts from oxygen depletion and disease spread. In cities, water loss from leaks can be a major issue, and fixing hidden pipe breaks can save large volumes of treated water. Water that already requires energy, chemicals, and infrastructure to make it safe. When a river has access to a broad, flat valley, it can slowly curve back and forth instead of cutting straight. These bends are called meanders, and they form because water moves faster along the outside of a curve and slower along the inside. Faster water has more energy to erode the bank, while slower water drops some of its sand and silt. Over time, that gentle imbalance makes the curve grow and walk sideways across the landscape. An oxbow lake is created when a meandering river takes a shortcut. As a bend becomes tighter, the river may eventually break through the narrow neck of the curve during a flood or a period of high flow. The main current then chooses the shorter, straighter path, and the old loop is left behind. The abandoned loop can fill with still water and become a crescent-shaped lake, showing a quiet record of where the river once flowed. Groundwater is simply water that has moved down into the ground and is stored in the tiny spaces between particles of soil or in cracks within rock. Even though it is hidden, it is a major part of the fresh water people use for drinking and farming. Groundwater can also feed streams and wetlands, especially during dry seasons, when rainfall is low but water continues to seep slowly into river channels. An aquifer is an underground layer that can both store water and let it move through. Some aquifers are made of sand and gravel, where water flows through spaces between grains, while others are made of fractured rock, where water travels through networks of cracks. The type of aquifer matters because it determines how quickly water can be pumped out, how easily it can be recharged, and how vulnerable it is to pollution from the surface. Recharge is the process that refills groundwater supplies. It happens when rain or melted snow soaks into the ground instead of running off the surface, and then continues downward until it reaches saturated zones. Recharge can be slow in dense clay soils and faster in sandy soils or fractured rock. Land use also matters. Forests and open soil often allow more infiltration than paved city surfaces. A spring forms when groundwater finds a natural pathway back to the surface. This can happen where the water table intersects the land, or where layers of rock guide water sideways until it emerges on a hillside or in a valley. Springs can range from tiny seeps to powerful flows that feed rivers. Many ecosystems rely on springs because they provide steady water even when rain is scarce. Artesian conditions occur when groundwater is trapped in a confined aquifer between less permeable layers and the water is under pressure. If a well is drilled into that confined layer, the pressure can push water upward, sometimes rising above the top of the aquifer without pumping. In certain locations, that pressure is strong enough for water to flow out at the surface. It's a clear reminder that underground water is not just stored. It can also be pressurized and moving. The water table is the boundary below which the ground is fully saturated with water. Above it, soil still contains air pockets as well as moisture, but below it, the spaces are filled with water. The water table is not fixed. It rises after wet seasons and falls during droughts. When wells pull water faster than the ground is recharged, the water table can drop, making it harder to access groundwater. In coastal areas, freshwater aquifers can be threatened by seawater intrusion when groundwater is pumped too heavily. Normally, freshwater underground helps keep seawater back because it is slightly less dense and forms a protective freshwater lens. But if pumping lowers the freshwater level, salty seawater can creep inland through the aquifer. This makes the water too salty to drink or use for many crops without treatment, and reversing it can be slow. Karst landscapes form when water dissolves soluble rocks, especially limestone. Rainwater absorbs carbon dioxide from the air and soil, becoming mildly acidic, and over long periods it can dissolve limestone along cracks and joints. This creates caves, sinkholes, and underground channels where water can flow quickly. Because karst systems can move water fast, they can also be more vulnerable to contamination, since pollutants may travel farther with less natural filtering. Some groundwater moves so slowly that it can take years, centuries, or even longer to travel from where it enters the ground to where it emerges. The speed depends on the rock type, the slope of the water table, and the size of the pathways underground. In fine-grained sediments, water can creep through tiny pores at a very slow pace. This slow movement is one reason some deep groundwater can represent very old stored water. Soil moisture is the water held in the upper layers of ground, above the saturated zone. This moisture is essential for plant growth because roots draw water from it. Soil moisture also controls how much rain turns into runoff versus how much sinks into the ground. When soil is already saturated, even moderate rain can cause flooding, but when it is dry, much more water can soak in. Capillary action helps water move through narrow spaces in soil. Because water molecules cling to each other and to soil surfaces, they can rise or spread through tiny pores, even against gravity for short distances. This is why soil can remain damp below the surface, even when the top layer looks dry. Capillary movement also helps distribute water toward plant roots, making moisture available across small distances. Plants release water vapor through transpiration, which is like a slow, steady breathing of moisture into the air. Water is pulled up from roots through plant tissues and exits through small openings in leaves. This process cools the plant and helps move nutrients. On a large scale, transpiration adds moisture to the atmosphere and can influence local humidity and even rainfall patterns. The water cycle includes evaporation, condensation, precipitation, runoff, infiltration, and transpiration. And it links the ocean, the atmosphere, and the land into one connected system. Water evaporates into invisible vapor, forms clouds as it condenses, and falls again as rain or snow. Some of that water runs across the surface into rivers, while some sinks into the ground to become groundwater. This cycle is always moving, even when it feels quiet. Oceans supply a major fraction of atmospheric water vapor through evaporation. Sunlight warms the surface, and energetic water molecules escape into the air, carrying heat with them. Winds then move that moisture around the planet. This is why coastal regions often have humid air, and why storms can draw strength from warm ocean surfaces that provide both water vapor and energy. Most precipitation falls back into the oceans, while a smaller portion falls on land. The land portion is still crucial because it feeds rivers, lakes, soil moisture, and groundwater, the sources people depend on for daily life. From there, water returns to the ocean through rivers and groundwater discharge. Even though the land share is smaller, it is the part that interacts most directly with ecosystems, farms, and cities. Snowpack can act as seasonal water storage, holding winter precipitation and releasing it later as it melts. This slow release is important because it spreads water supply across the warmer months when plants grow and rivers might otherwise be low. In many mountain regions, snowpack is like a natural reservoir, and the timing of melt strongly affects water availability downstream. Glaciers store fresh water for long periods, and their melt can help sustain rivers during dry seasons. When a glacier melts, it releases water that has been stored as ice, sometimes for decades or longer. This can keep rivers flowing even when rainfall is low. However, if a glacier shrinks over time, the long-term water contribution can eventually decline, changing river behavior. Sea ice is frozen seawater, while glacial ice usually forms from compacted snow on land. This difference matters because sea ice is part of the ocean surface system, growing and shrinking with seasonal temperatures, while glaciers are land-based ice bodies that flow under gravity. When sea ice melts, it does not add much to sea level because it was already floating. When glaciers melt, they can add water to the ocean and raise sea level. When sea ice forms, it tends to exclude much of the salt, creating cold, salty brine that can sink into deeper layers. This makes nearby seawater denser and can contribute to the formation of deep ocean water masses. Those sinking waters help drive large-scale ocean circulation. In that way, the freezing process doesn't just create ice at the top, it can also influence movement far below the surface. Ocean circulation includes surface currents driven by winds and deep circulation influenced by temperature and salinity differences. Surface currents move heat around, warming some coasts and cooling others. Deep circulation is slower and depends on dense water sinking in cold regions and rising elsewhere. Together, these movements help mix nutrients, distribute oxygen, and shape climate patterns over long distances and long times. Thermohaline circulation is the name for the global-scale movement of ocean water, driven by temperature and salinity. Cold, salty water is dense and tends to sink, while warmer or fresher water is lighter and tends to stay near the surface. This creates a broad conveyor-like pattern that connects different ocean basins. It moves heat from the tropics toward higher latitudes and helps the ocean store and transport energy. Water covers about 71% of Earth's surface, which is why the planet appears mostly blue from space. This vast coverage affects more than scenery. It shapes climate, weather, and how heat is stored and moved around the globe. Large water surfaces also drive evaporation, cloud formation, and rainfall patterns. Even far inland, many weather events trace back to ocean conditions. The oceans hold about 96.5% of Earth's water by volume, so most of the planet's water is salty and part of a single connected system. That huge reservoir exchanges water with the atmosphere through evaporation and with land through precipitation and river flow. It also absorbs and releases heat slowly, influencing climate. Because of this, changes in the ocean can have planet-wide effects. Only a small fraction of Earth's water is fresh water, and most of that fresh water is stored in glaciers, ice sheets, and groundwater. This means the easy-to-see freshwater rivers and lakes is only a thin slice of what exists. It also means freshwater availability can be sensitive to changes in ice melt, groundwater recharge, and regional rainfall. Managing freshwater well often depends on understanding those hidden stores. Rivers and lakes contain a tiny share of Earth's total water compared with oceans, ice, and groundwater. Even so, they are among the most important waters for daily life and ecosystems because they are accessible and constantly renewed by the water cycle. Their small volume also means they can be influenced quickly by pollution, drought, or overuse. Protecting them has a large payoff because they serve so many needs. The atmosphere holds water vapor and clouds, but the total amount of water in the air is small compared with oceans and groundwater. Even so, atmospheric water is extremely active, moving and changing quickly. It can turn into clouds, fall as rain, and evaporate again in a short time. That fast cycling is part of why weather can shift from dry to stormy within hours or days. Because the atmosphere contains a limited amount of water, changes in humidity can happen quickly as air masses move and temperatures change. Warm air can hold more water vapor, so a warming day can lower relative humidity, even if the water vapor amount stays the same. Cooler air can reach saturation more easily, leading to dew, fog, or clouds. This is why temperature and moisture are so tightly linked in everyday weather. Most freshwater in many regions comes from the cycling of water, rather than from a large standing supply in the air. Water vapor is constantly transported by winds, condensed into clouds, and released again. This makes the atmosphere more like a fast-moving delivery system than a storage tank. The real storage tends to be oceans, groundwater, snowpack, and ice, while the air acts as the quick messenger. Desalination removes salts from seawater or brackish water, making it usable for drinking or irrigation. The most common approach today is reverse osmosis, where pressure pushes water through a membrane that blocks many dissolved salts. The process can provide a reliable supply in dry regions, but it also needs energy and careful handling of concentrated salty brine. For many places, it is one tool among several for meeting water demand. Reverse osmosis works by using high pressure to force water through a semi-permeable membrane. The membrane allows water molecules to pass but blocks many dissolved ions and larger contaminants. Because seawater is naturally salty, it resists this flow, so pumps must work hard to overcome the natural osmotic pressure. The result is fresh water on one side and concentrated brine on the other, which must be managed responsibly. Thermal desalination separates water from salts by heating water until it becomes vapor, and then condensing it back into liquid. Because salts do not evaporate with the water, the condensed vapor becomes fresh water. This method can be effective, especially where waste heat is available, but it often uses more energy than membrane-based methods. Different regions choose different approaches based on fuel costs, infrastructure, and water needs. Desalination requires significant energy, so many facilities focus on efficiency and careful planning. Energy recovery devices can capture some of the pressure energy in reverse osmosis systems and reuse it, lowering power needs. Operators also monitor membranes to reduce fouling and maintain performance. The goal is to make each liter of water as energy efficient as possible, because energy costs strongly shape the practicality of desalination. A major environmental issue in desalination is the brine that remains after fresh water is removed. This brine is saltier than seawater and may also contain treatment chemicals. If released improperly, it can affect marine life near discharge points. Many modern systems use diffusers, blending, or careful siting to reduce impacts and protect coastal ecosystems. Drinking water treatment often uses multiple steps because water can contain many kinds of impurities, particles, microbes, and dissolved chemicals. A typical system may first remove debris and settle out solids, then filter finer particles, and finally disinfect to reduce pathogens. Each stage supports the next, and together they make the system more robust. This layered approach helps protect public health even if water quality changes with seasons. Coagulation and flocculation help tiny particles in water stick together so they can be removed more easily. Water can contain very small suspended particles that do not settle quickly on their own. By adding coagulants, those particles lose their electrical repulsion and begin to clump into larger flocks. Once clumped, they can settle out or be captured by filters, leaving the water clearer and easier to disinfect. Filtration can be done using sand, other granular materials, or membranes, depending on the treatment goal. Sand filters trap particles as water moves through the spaces between grains, and biological layers can also form that help remove some contaminants. Membrane filters can have very small pores and can remove finer material, but they need maintenance and can be more energy intensive. The choice depends on the water source and the level of treatment required. Chlorine is widely used as a disinfectant because it can kill many bacteria and viruses and can remain in the water as a protective residual. That residual matters because water often travels through pipes for hours or days after leaving the plant. A small chlorine level can help prevent microbial regrowth during distribution. Utilities carefully control dose because too little reduces protection and too much can affect taste or create unwanted byproducts. A drawback of chlorination is that chlorine can react with natural organic matter in water and form disinfection byproducts. These byproducts are one reason utilities work hard to remove organic material before disinfection and to optimize chlorine dosing. Water quality regulations often set limits on certain byproducts, pushing treatment plants to balance safety against chemical side effects. This is part of why treatment is designed as a system, not a single step. Ultraviolet disinfection inactivates microbes by damaging their genetic material, so they cannot reproduce. UV is effective against many pathogens and works quickly as water passes by UV lamps. It does not leave a long-lasting residual in pipes, so some systems pair UV with a small amount of chemical disinfectant to protect water during distribution. UV systems must also ensure water is clear enough, because particles can shield microbes from UV light. Ozone is a strong oxidant used in some water plants to inactivate microbes and break down certain chemical contaminants. It can be very effective, including against some organisms that are harder to control with chlorine alone, Because ozone does not remain in water for long, it is often used as part of a multi-step process. After ozonation, some systems add a secondary disinfectant to maintain protection in the distribution network. Household-level disinfection can reduce disease risk, where centralized treatment and safe distribution are limited. Simple approaches, such as boiling, chlorination with measured doses, or certain filtration methods can lower exposure to pathogens. However, the effectiveness depends on correct use and safe storage afterward. Even treated water can become contaminated again if stored in open or unclean containers. Safe storage matters because water can be recontaminated after treatment through hands, cups, or containers. Using clean covered containers with narrow openings can reduce contact with dirt and pathogens. Pouring instead of dipping helps keep the water safer over time. In places without reliable infrastructure, safe storage can be as important as the treatment step itself. Boiling kills many pathogens because high heat damages their proteins and genetic material. It is reliable for microbes, but it does not remove dissolved salts and usually does not remove many chemical contaminants like certain metals. Boiling can also concentrate some dissolved substances if water evaporates and is not replaced. This is why boiling is best understood as a microbial safety measure, not a full purification method. Water is a polar molecule, which means its electrical charge is not spread evenly. The oxygen side carries a slight negative charge, while the two hydrogen sides carry slight positive charges. This unevenness makes water behave like a tiny magnet, so it naturally lines up around other charged or polar substances. That single feature is a big reason water interacts so strongly with salts, sugars, proteins, and many materials in the world around us. Hydrogen bonds are gentle attractions that form when the slightly positive hydrogen of one water molecule is drawn toward the slightly negative oxygen of another. Each bond is much weaker than the strong covalent bonds inside a molecule, but in liquid water they form and break constantly in enormous numbers. This shifting network helps explain why water can flow while still holding together, why it has an unusually high boiling point for such a small molecule, and why it behaves differently than many other common liquids. Cohesion is water's tendency to stick to itself because water molecules attract one another through hydrogen bonding. In practical terms, cohesion helps water form continuous streams, rounded droplets, and stable columns in very small spaces. It also means water can resist being pulled apart, which matters in everything from raindrop formation to how water moves through narrow channels. Adhesion is water's tendency to stick to other materials, especially those with charged or polar surfaces. When water meets glass, plant tissue, or many minerals, the molecules can cling to the surface instead of beading up. Adhesion is one reason water wets many surfaces and spreads into thin films. In nature, adhesion helps water coat soil particles and flow along surfaces in tiny pathways. Surface tension is created because molecules at the surface of water are pulled inward by neighboring molecules, forming a tight elastic-like layer. This is not a solid skin, but it acts like one in small-scale situations. It allows small objects to rest on the surface if they don't break the surface layer. Surface tension also shapes droplets, supports bubbles, and influences how water breaks apart into sprays. Some small insects can stand or skate on water because the surface tension supports their weight and their legs are adapted to avoid piercing the surface. Many have fine hairs or waxy coatings that repel water, helping them distribute weight over a larger area. If the surface is disturbed with soap or oils that reduce surface tension, the same insects can struggle because the supportive film becomes weaker. It's a clear example of how water's molecular attraction becomes a visible force. Water is often called a universal solvent because it dissolves a wide range of substances, especially ionic and polar compounds. This happens because water's polar structure lets it surround and separate charged particles or interact with polar molecules. It does not dissolve everything. Oils and many non-polar materials resist mixing with water, but it dissolves enough substances to make it a central medium for chemistry in nature and in living organisms. When salts dissolve in water, they separate into ions, and water molecules organize around those ions to form hydration shells. The oxygen side of water faces positive ions, and the hydrogen sides face negative ions. This stabilizes the ions in solution and keeps them from snapping back together immediately. Hydration shells are also important in biology because many cellular processes depend on ions moving through watery environments. Pure water is actually a poor conductor of electricity because electrical conduction in water mostly comes from dissolved ions. When water contains salts, acids, or other ion-producing substances, it can carry electrical current much more easily. This is why seawater conducts electricity far better than distilled water. It also helps explain why water safety depends strongly on what is dissolved in it, not just the water itself. pH is a measure of how acidic or basic a solution is, based on the concentration of hydrogen ions. Pure water at room temperature is often close to neutral, but natural waters can shift more acidic or more basic depending on dissolved gases and minerals. For example, dissolved carbon dioxide can make water slightly more acidic, while certain rock minerals can buffer water toward higher pH. pH matters because it affects corrosion, metal solubility, and which organisms can thrive. When carbon dioxide dissolves in water, it can form carbonic acid, which gently lowers the pH. This mild acidity is enough to help dissolve certain rocks over long periods, especially limestone. It also plays a role in ocean chemistry because the ocean absorbs carbon dioxide from the atmosphere. The balance among dissolved CO2, carbonic acid, and carbonate forms is a key part of how water interacts with the carbon cycle. Hard water contains higher amounts of calcium and magnesium ions that water picks up as it passes through certain rocks and soils. These minerals are not usually harmful at typical levels, but they can cause scale in pipes and appliances. Hard water can also change how soap behaves, making it harder to form lather. The hardness is essentially a description of dissolved mineral content, not a texture of the water itself. Soft water has fewer calcium and magnesium ions, so it tends to lather more readily with soap and leaves less mineral scale behind. In homes, soft water can make cleaning easier and reduce buildup in kettles and heaters. Some regions naturally have soft water because of local geology, while others soften water using treatment systems. The difference is often noticeable in how quickly soap produces foam and how surfaces look after drying. Soap scum forms because traditional soaps can react with calcium and magnesium in hard water, producing insoluble compounds. Instead of staying dissolved and rinsing away, these compounds can deposit on surfaces as a dull film. That film can trap dirt and make surfaces look cloudy. This is why some cleaners and detergents are formulated to reduce these reactions and perform better in hard water. Water's viscosity is its resistance to flow, and it changes with temperature. Cold water is more viscous, so it flows more sluggishly, while warm water flows more easily. This matters in nature and technology, from how quickly streams respond in winter to how pumps and pipes perform at different temperatures. Even small viscosity changes can affect turbulence, mixing, and how particles settle. Water is slightly compressible, but far less than gases, which is why pressure changes travel efficiently through it. If you push on water in a sealed container, it compresses a tiny amount and transmits force through the whole volume. This property is used in hydraulic systems, where pressure is moved through liquids to do work. In the ocean, increasing pressure with depth also changes water's density slightly and influences how sound travels. Sound travels faster in water than in air, but the speed depends on temperature, salinity, and pressure. Warmer water generally allows faster sound transmission because molecules move and transmit vibrations more readily. Higher salinity and higher pressure also tend to increase sound speed. This is important for marine mammals, submarine navigation, and scientific measurements that use sound to map the seafloor. Water can hold dissolved gases, such as oxygen, nitrogen, and carbon dioxide, which allows aquatic life to breathe and helps regulate chemical balance. Fish and many invertebrates rely on dissolved oxygen, withdrawing it from water through gills or other surfaces. The ability of water to carry gases also means gas levels can shift with temperature, mixing, and biological activity. Even a small change in dissolved oxygen can strongly affect aquatic ecosystems. Colder water can hold more dissolved oxygen than warmer water, which is why some species prefer cooler habitats. In warm conditions, oxygen solubility drops, and organisms may also use oxygen faster because metabolism increases with temperature. This combination can create stress during heat waves, especially in stagnant waters. It's a clear example of how a basic physical property of water shapes biological life. Stratification happens when water layers form because of density differences, often driven by temperature or salinity. In a stratified lake, warm, lighter water can sit above cooler, denser water, reducing mixing between layers. This can limit oxygen reaching deeper zones and trap nutrients below. Stratification can be stable for months, and then seasonal cooling or wind can break it and mix the lake again. In some lakes, seasonal mixing, often called turnover, redistributes oxygen and nutrients through the whole water column. As surface water cools and becomes denser, it can sink and bring deeper water upward. This mixing supports aquatic life by replenishing oxygen in deeper layers and bringing nutrients into sunlit zones. The timing and strength of turnover can shape fish habitat and overall lake health. Water reaches its maximum density at about 4 duffant, which creates a special behavior in freshwater lakes during cold seasons. As a lake cools from summer warmth, water near the surface becomes denser and sinks until it approaches 4 duffant. If it cools further, it becomes slightly less dense and stays near the top, allowing the surface to reach 0 duffant freeze while deeper water remains liquid. This is one reason many lakes can support life through winter under ice. Evaporation can happen below the boiling point because molecules at the surface can escape when they have enough energy. Not all molecules have the same energy at the same temperature, so some are always energetic enough to leave the liquid. Wind and low humidity help carry away those escaped molecules, allowing more evaporation to continue. This quiet surface process is one of the main ways water moves from oceans and lakes into the atmosphere. Boiling is different from evaporation because it forms vapor bubbles inside the liquid, not just at the surface. For bubbles to form and grow, the pressure of the vapor inside must match the surrounding pressure. That's why boiling depends strongly on atmospheric pressure. At sea level, water boils around 100 surface, but at high elevations it boils at lower temperatures because the pressure is reduced. At higher elevations, water boils at a lower temperature, which can change cooking and industrial processes. Because boiling temperature is lower, foods that require higher heat may cook more slowly unless pressure is increased. This is why pressure cookers can be helpful at altitude. The key idea is simple. Lower pressure makes it easier for water molecules to turn into gas. A pressure cooker raises the boiling point of water by increasing the pressure inside the pot. When pressure rises, water needs a higher temperature to boil, so liquids can get hotter than 100 degrees without rapidly turning to steam. That extra heat speeds cooking by delivering more thermal energy into food. It is a practical use of the relationship between pressure and phase change. The speed of evaporation increases when temperature is higher, humidity is lower, surface area is larger, and air movement is stronger. Warm molecules escape more easily. Dry air can accept more vapor, and wind removes humid air near the surface. A shallow, wide pan loses water faster than a deep, narrow container because more water is exposed. These simple factors explain why puddles disappear faster on hot, breezy days than on cool, still days. Water vapor is invisible, and what people often call steam is actually a cloud of tiny liquid droplets formed when vapor cools and condenses. When hot water is boiling, vapor rises but quickly meets cooler air and condenses into a visible mist. That mist is made of fine droplets suspended in air. The true gas phase of water remains unseen, even when present in large amounts. Condensation releases heat to the surrounding air because molecules give up energy when they switch from gas to liquid. This release of latent heat is a major driver in weather systems. When water vapor condenses into clouds, it can warm rising air and help it continue rising, strengthening storms. It is one of the key ways the atmosphere moves energy from one place to another. Supercooled water droplets can remain liquid below 0 if they lack the right trigger to freeze. In clouds, tiny droplets can stay liquid well below freezing until they contact a particle or a surface that helps ice crystals form. When freezing does occur, it can happen quickly and spread through nearby droplets. This behavior matters for cloud physics, icing on aircraft, and how certain types of precipitation form. Snow can form when water vapor deposits directly into ice crystals, or when supercooled droplets freeze and attach to crystals as they fall. The shape of snow crystals depends on temperature and humidity, producing many different patterns. As crystals collide and stick, they form flakes that can become large and complex. The entire process is a delicate expression of how water changes phase in the atmosphere. Dew forms when surfaces cool enough at night for nearby air to reach saturation, causing water vapor to condense as droplets. Grass, car roofs and other surfaces can cool by radiating heat into the night sky. When the surface temperature drops below the dew point, moisture condenses. Dew is a simple, everyday demonstration of how temperature controls the air's capacity to hold water vapor. Frost forms when water vapor deposits directly as ice on a surface that is below the frost point. Unlike dew, which forms liquid droplets first, frost can appear as crystals when temperatures are cold enough. The patterns often look feathery because ice crystals grow outward in branching shapes. Frost shows another pathway in the water phase system, gas turning straight into solid. Water bends light as it enters because it has a refractive index different from air. This is why objects underwater can appear shifted, magnified, or closer than they really are. Refraction also helps create optical effects, such as the shimmering look of sunlit water surfaces. Even simple experiences, like a straw appearing bent in a glass, come from how water slows and redirects light. Water absorbs red light more strongly than blue light, which contributes to the blue appearance of deeper, clearer water. As sunlight penetrates water, longer red wavelengths are removed more quickly, leaving more blue light to scatter back to our eyes. In very clear oceans, this effect is stronger, producing rich blue tones. In murky or algae-rich water, suspended particles and pigments can change the apparent color. Water's cohesion and adhesion together make capillary action possible, where water can rise or move through narrow spaces. In a thin tube or tiny pore, water molecules cling to the surface and pull other water molecules along. This can move water upward against gravity for small distances. Capillary action is important in soils, in paper towels, and in plant tissues where water moves through microscopic channels. The Leidenfrost effect occurs when a water droplet hovers on a thin layer of its own vapor over a very hot surface. The bottom of the droplet vaporizes instantly, creating a cushion that reduces direct contact with the hot plate. Because the droplet is insulated by vapor, it can survive longer than you might expect. This effect is a striking example of how phase change can create a physical barrier. Water expands when it freezes, which is unusual because many substances contract as they solidify. In ice, water molecules arrange into a more open crystal structure, held by hydrogen bonds. That structure takes up more space, lowering density and allowing ice to float. The expansion also explains why freezing water can crack rocks and burst pipes when confined. Freeze-thaw weathering happens because water can seep into cracks in rock, freeze, expand, and push the crack wider. Repeated cycles gradually break rock into smaller fragments, contributing to soil formation and shaping mountain slopes. The process is especially effective in climates where temperatures frequently cross the freezing point. It is a simple mechanical effect powered by water's expansion during freezing. Water's behavior as a solvent supports countless chemical reactions, including hydrolysis, where water helps break large molecules into smaller ones. In hydrolysis, a water molecule can split into components that attach to different parts of a larger molecule, helping it separate. This is central in digestion, where complex foods are broken down into usable building blocks. It also occurs widely in natural weathering, and biochemical cycles. Because pure water does not conduct electricity well, changes in conductivity are often used to infer how many ions are dissolved in water. Scientists and water managers measure conductivity to track salinity changes, pollution events, or mixing of waters. For example, a sudden rise in conductivity in a freshwater stream can indicate an influx of salty runoff. It's a simple measurement that reveals important chemical information. Water's surface tension can be reduced by substances like soaps and detergents, which is why they help cleaning. These molecules have one end that likes water and another that avoids it, so they collect at surfaces and disrupt the tight hydrogen-bonded network. Reduced surface tension helps water spread into thin layers and penetrate fabrics or tiny crevices. It also helps break up oily residues by forming micelles that trap oil droplets. Oil and water do not mix easily because oil molecules are mostly non-polar, while water is polar. Water's molecules prefer bonding with each other rather than surrounding non-polar molecules, so oil separates into droplets. Detergents solve this by surrounding oil with structures that can interact with both oil and water. This everyday separation is a direct consequence of water's polarity and hydrogen bonding. Water's heat of vaporization is the reason evaporation can produce strong cooling, even without boiling. When the most energetic molecules escape as vapor, they take a large amount of heat energy with them. The remaining liquid has lower average energy, so it cools. This is why evaporation from skin can cool the body and why coastal winds can feel cooler when they carry moisture away. Water's specific heat is why it takes longer to warm up a lake than the surrounding land in spring. The same sunlight energy that quickly heats soil will raise water temperature more slowly. This property smooths temperature swings near large water bodies, producing milder coastal climates. It is a quiet thermal stability that comes from how water molecules store energy through their bonding and motion. Even small changes in temperature can alter how much water vapor air can hold, which is why humidity and weather are closely tied to physics. Warmer air increases the maximum possible water vapor content, while cooler air lowers it and encourages condensation. This is why cooling a humid air mass can lead to clouds and rain. The relationship between heat and water vapor is one of the most basic drivers behind storms and precipitation patterns. In food science, water activity describes how much of the water in a food is actually available for microbes to use, not just how wet the food seems. Some water can be tightly bound to sugars, salts, or proteins, and microbes can't easily access it. When water activity is high, many bacteria, yeasts, and molds can grow more readily. When it's low, growth becomes much harder, which is why this single measurement is so useful for predicting shelf life. Drying and salting foods work partly because they reduce the amount of available water that microbes need to survive and multiply. Drying removes moisture, so cells struggle to function, while salt can draw water out of microbial cells through osmosis. This slows or stops growth even if the food still contains some moisture. It's an old preservation idea, but it's based on very precise physical behavior of water around dissolved substances. In coffee and tea, the mineral content and pH of water can change how flavors are extracted from the beans or leaves. Minerals can interact with flavorful compounds and influence which ones dissolve more easily. Water that is too soft or too hard can make drinks taste flat, overly sharp, or oddly muted. This is why the same coffee can taste noticeably different in different cities, even if everything else is identical. In brewing, water hardness and alkalinity influence mash chemistry, which affects how enzymes break down grains and how flavors develop. Alkalinity can buffer pH changes, and pH strongly affects enzyme performance during mashing. If the pH is too high or too low, the conversion of starches to sugars can become less efficient. Brewers often adjust water chemistry to help fermentation, clarity, and taste stay consistent. Aquariums need careful water management because fish and aquatic plants are sensitive to temperature, pH, hardness, and nitrogen compounds. If pH swings quickly, fish can become stressed because their bodies must constantly adjust salt and acid balance. Hardness affects mineral availability, and can influence species comfort. Temperature changes alter oxygen levels and metabolism, so stable water conditions are one of the strongest foundations of aquarium health. The nitrogen cycle in water includes transformations among ammonia, nitrite, and nitrate, and bacteria are often the main drivers of these changes. Fish waste and decaying food can produce ammonia, which is harmful at high levels. Specialized bacteria convert ammonia into nitrite, which can also be toxic, and then into nitrate, which is usually less harmful in moderate amounts. Managing this cycle is why filtration and regular maintenance matter so much in closed water systems. Dissolved organic matter can make natural waters look brown or tea-colored, especially where water flows through peat-rich soils or forested wetlands. This organic material includes many complex molecules from decaying plants. It changes how sunlight penetrates the water, which can affect aquatic plants and temperature patterns. It can also influence taste and treatment needs in drinking water sources. Microplastics can travel in water when larger plastic items break into smaller fragments and fibers. Their distribution depends on how water moves, currents in the ocean, runoff during storms, and even wind-driven surface flow. Some microplastics float, some sink, and some move up and down as they collect biological growth or attach to particles. This means their pathways can be complex, and they can show up in places far from where the plastic first entered the environment. Ocean currents can concentrate floating debris in certain regions, creating areas where plastics and other materials become more common. These zones form because surface currents and winds can circulate in broad loops that slowly gather drifting items. The debris doesn't always form a solid island, but concentrations can become much higher than surrounding waters. The same physical processes that move heat and nutrients can also gather floating pollution. Freshwater systems can also collect plastics, often in river bends, wetlands, and lake shorelines where water slows down. When flow speed drops, floating and suspended materials have more time to accumulate. Vegetation can trap debris, and muddy shorelines can hold plastics in place until the next storm. This makes certain calm areas act like collection points, even in places that look clean at first glance. Because rivers transport sediment, they can move not only nutrients but also pollutants that stick to particles. Many contaminants don't travel as dissolved chemicals. Instead, they attach to clay, silt, or organic matter. When those particles settle, the contaminants can settle too, creating hotspots in riverbeds, reservoirs, or deltas. Understanding particle transport is essential for predicting where pollution will end up. Heavy metals can bind to sediments, which means the riverbed can become a long-term storage zone for contamination. Metals may stay locked in place under stable conditions, but changes in water chemistry or strong disturbances can release them back into the water. Dredging, floods, or shifts in oxygen levels can all influence how tightly metals remain bound. This is why sediment testing can be as important as testing the water itself. Water treatment plants may adjust pH and alkalinity to reduce corrosion, because corrosive water can dissolve metals from pipes. If water is too acidic or lacks buffering capacity, it can slowly eat away at plumbing materials. By adjusting chemistry, utilities can encourage protective mineral layers to form inside pipes, which reduces metal release. This is a quiet but critical part of keeping water safe between the plant and the tap. When corrosion control is done well, it can reduce the release of lead and copper into drinking water from household or city plumbing. The goal is often to stabilize the pipe interior, so metals are less likely to dissolve. This may involve controlling pH, alkalinity, and adding corrosion inhibitors that support protective coatings. It's a reminder that safe water is not only about treatment at the plant, but also about how water behaves while traveling through infrastructure. Chlorine taste and odor can vary depending on how much chlorine is used, how much organic matter is in the water, and how long the water has spent in the distribution system. If water sits longer in pipes or tanks, chlorine levels can change over time. Organic materials can also consume chlorine, altering both disinfectant strength and sensory qualities. Utilities balance these factors so water remains protected without strong or unpleasant taste. River discharge is often measured in cubic meters per second, which captures how much water passes a point over time. This measurement helps describe a river's power and its ability to carry sediment, shape channels, and support ecosystems. High discharge can mean increased flood risk, while low discharge can mean stress for fish and reduced water supply. Discharge is one of the most basic numbers used in river science and water management. Stream gauges help forecast floods and manage water resources by tracking river level and flow, often continuously. By comparing current readings with historical patterns, agencies can estimate how quickly water is rising and how severe flooding might become. Gauges also help water managers plan reservoir releases and track drought conditions. A simple sensor at the river can support decisions that affect entire regions downstream. Water's high heat capacity makes it useful in thermal energy storage because it can store large amounts of heat with only modest temperature change. This allows systems to collect heat when it's available and release it later when needed. For example, heated water tanks can store energy from off-peak electricity or from solar collection. The stability of water temperature makes these systems predictable and practical. Many solar thermal systems use water or water-based fluids to capture and transport heat from sunlight. Water can absorb heat in collectors and then carry it to a storage tank or a heat exchanger. Sometimes additives are used to prevent freezing or corrosion, depending on climate and system design. The central idea is simple. Water's thermal properties make it an efficient carrier of heat. In hydronic heating, hot water circulates through radiators or floor tubing to deliver heat gently and evenly. Water carries heat from a boiler or heat pump to different rooms and then returns to the cooler to be reheated. Because water can carry a lot of heat, these systems can be efficient and comfortable. Many people experience hydronic heat as steady and quiet compared with forced air systems. Cooling towers use evaporative cooling, which relies on water's large heat of vaporization. When a small portion of water evaporates, it removes a large amount of heat from the remaining water. That cooled water can then be reused to absorb more heat from industrial equipment or building systems. It's a controlled version of the same physics behind sweat evaporating from skin. Water can serve as a radiation shield in some nuclear applications because it can slow and absorb certain particles. Its density and hydrogen content make it useful for reducing the energy of neutrons and absorbing radiation energy. Large water pools can both cool equipment and provide shielding at the same time. This is a practical example of how water's basic physical properties become safety tools in engineering. Water helps fight fires by absorbing heat, and when it turns to steam, expanding and helping reduce oxygen near flames. Cooling is often the main benefit, lowering the temperature of burning materials so combustion slows or stops. Steam formation can also help separate fuel from oxygen in certain conditions. Firefighting methods are designed around these thermodynamic effects of water. Water mist systems can suppress fires by using very fine droplets that absorb heat quickly and reduce radiant heat transfer. Smaller droplets have a large surface area, so they can evaporate efficiently and cool hot gases. This can lower temperatures and make the environment less supportive of sustained burning. Mist systems are especially useful in certain enclosed spaces where rapid cooling is valuable. The Leidenfrost effect happens when a water droplet skates on a thin cushion of its own vapor above a very hot surface. The bottom layer flashes into vapor and creates insulation, reducing direct contact with the surface. Because of that insulating vapor layer, the droplet can last longer and move around as if it's floating. It's a clear demonstration of how phase change can create a temporary barrier between liquid and solid. Water's density and viscosity affect how quickly particles settle, which shapes sediment layers in lakes and oceans. In calmer water, particles have time to sink and form layers, while in turbulent water, they stay suspended longer. Temperature also changes viscosity, which changes settling speed slightly. Over long periods, these small physical effects help build the layered records found in sediments. Varves are seasonal sediment layers in some lakes, often forming a pair of layers each year, one from a season of higher energy and one from calmer conditions. Over time, they create a natural timeline, like a stack of pages recording yearly changes. Scientists can count valves and analyze their composition to infer past conditions such as runoff intensity or biological productivity. It's a patient archive written by settling particles in water. Ice cores preserve tiny bubbles of ancient air and chemical signals, providing direct evidence of past atmospheric conditions. As snow falls and compresses into ice, it can trap small pockets of air. Over time, those pockets become sealed, storing samples of older atmospheres. By studying the gases and impurities, researchers can reconstruct changes in climate and greenhouse gases over long time spans. Water isotopes, such as oxygen-18 and deuterium, vary with temperature and precipitation patterns, making them powerful tools for reconstructing past climates. When water evaporates and condenses, lighter and heavier isotopes behave slightly differently. This creates predictable patterns in snow, rain, and ice depending on the conditions under which they formed. By measuring isotope ratios in ice cores and other records, scientists can infer how temperature and moisture sources changed through time. Water in clouds can have different isotope ratios depending on the path the vapor took and how it condensed. Vapor that traveled far, rose to high altitudes, or went through repeated condensation events can become fractionated, meaning its isotope mixture shifts. These subtle differences can be measured and used to study moisture transport and storm origins. It's a fine-scale fingerprint that helps connect cloud water to larger atmospheric processes. In medicine, intravenous fluids are water-based solutions with carefully controlled electrolytes so they match the body's needs. Pure water alone is not safe to infuse because it can disrupt salt balance and harm cells. By adjusting sodium, chloride, and other ions, clinicians can support blood volume, hydration, and acid-base balance. These fluids show how closely water and dissolved salts work together in human physiology. Osmosis is the movement of water across a semi-permeable membrane from the side with lower solute concentration toward the side with higher solute concentration. You can think of it as water moving to balance concentrations when a barrier lets water pass, but blocks many dissolved substances. Osmosis is one reason cells must control their internal salt balance so they don't swell or shrink. It's also the physical principle behind many filtration and biological processes. Cells maintain osmotic balance because large shifts in surrounding solute concentration can cause water to move in or out rapidly. If the outside is too salty, water can leave the cell and the cell can shrink. If the outside is too dilute, water can rush in and the cell can swell, sometimes to the point of damage. Organisms regulate salts and water carefully to keep conditions stable for proteins and membranes to work properly. Dialysis uses controlled membranes and fluids to remove waste products when kidneys cannot, relying on diffusion and water-based transport. Blood is brought close to a membrane where certain molecules can pass while others are kept inside. Waste products move into the dialysis fluid because of concentration differences, while important components are retained. The process depends on water's role as a solvent and on the predictable movement of dissolved substances. Environmental DNA sampling can detect organisms by finding traces of genetic material they leave in water, such as shed cells or fragments. Instead of catching or directly observing an animal, researchers can collect water and analyze it for DNA signatures. This can reveal the presence of rare, elusive, or early invading species. It's an example of how water quietly carries biological information that can be measured with modern techniques. Many aquatic organisms time reproduction to water conditions, like temperature, flow, and salinity, because these factors influence survival of eggs and young. Warmer temperatures can speed development, while flow can carry larvae to suitable habitats or wash them away. Salinity changes can stress sensitive life stages or determine where juveniles can thrive. By synchronizing with the right water conditions, organisms increase the odds that offspring will find food, oxygen, and shelter. Some polar summer melt ponds form on sea ice and change how much sunlight the surface absorbs. Darker ponded water absorbs more solar energy than bright ice, which can speed local melting. This creates feedback. More melting can create more ponding, which can further lower reflectivity. The process is subtle from a distance, but it can strongly influence seasonal ice behavior. Water's reflectivity depends on angle and surface roughness, which is why calm water can look mirror-like while rough water looks scattered and bright. At low angles, water can reflect a large portion of incoming light, producing glare. When waves roughen the surface, reflections scatter in many directions, changing the look and brightness. These optical properties also affect how satellites interpret water surfaces from above. Activated carbon can remove many taste and odor compounds because its surface is full of tiny pores that provide a very large area for molecules to stick to. When water passes through, certain organic chemicals and odor-causing compounds can be captured by adsorption, which is more like sticking to a surface than being filtered out by size. This is why activated carbon is commonly used to improve the sensory quality of water and to reduce some organic contaminants, even though it is not designed to remove everything. Some household water filters are built mainly to reduce chlorine taste and smell, while others are engineered for specific contaminants, such as lead, depending on how they are designed and what they are certified to remove. A filter that improves taste might do little for dissolved metals, and a filter designed for metals may require different materials and maintenance. The key point is that a filter is not one universal thing. Different filter media target different substances. This is why matching a filter type to the actual water issue matters for real protection. Water utilities monitor multiple parameters like turbidity, disinfectant levels, and microbial indicators because water quality can change as it moves from a source to a tap. Turbidity can signal how many suspended particles are present, and those particles can sometimes shelter microbes from disinfection. Disinfectant levels help confirm that the water still has protection while traveling through pipes. Microbial indicators are used because testing for every pathogen directly would be slow and complex. In distribution systems, leaks and pressure drops can increase contamination risks because water can be drawn inward through small openings when pressure falls. Under normal conditions, water pressure pushes outward, which helps keep outside contaminants from entering. But if pressure drops during a break, repairs, or heavy demand, nearby groundwater or soil water can be pulled into the pipe. This is why maintaining stable pressure and quickly repairing leaks is an important part of keeping delivered water safe. Primary wastewater treatment focuses on removing solids that can settle or float, using screens and settling tanks to separate out material. It is mainly a physical process that reduces the load of large particles. While it can remove a portion of pollution, it does not eliminate most dissolved organic matter. Primary treatment is often the first stage before more advanced biological steps. Secondary wastewater treatment uses microbes to consume dissolved and suspended organic material that would otherwise deplete oxygen in rivers and lakes. In aeration tanks or similar systems, bacteria break down organic compounds, converting them into biomass and simpler end products. This reduces the oxygen demand of the water once it is released. It's an engineered version of natural decomposition, sped up and controlled for environmental protection. Tertiary or advanced treatment can further reduce nutrients, micropollutants or pathogens, depending on what the water will be used for and where it will go. Some systems add filtration steps, specialized chemical processes, or additional disinfection. The goal might be cleaner discharge into sensitive ecosystems, safer reuse for irrigation, or preparation for groundwater recharge. Advanced treatment is chosen based on the specific risks and local needs. Removing nutrients like nitrogen and phosphorus from wastewater can help prevent downstream algal growth that would otherwise reduce oxygen when algae die and decompose. Nutrients are essential for life, but too much in the wrong place can destabilize water bodies. Treatment plants can use biological or chemical methods to capture and remove these nutrients. This reduces the likelihood of dense blooms and protects aquatic habitats. Reclaimed water can be used for irrigation, industrial cooling, or groundwater recharge when properly treated and regulated, which can reduce demand on scarce freshwater supplies. The level of treatment depends on the intended use because different uses have different safety requirements. For irrigation, the focus might be pathogens and certain chemicals. For groundwater recharge, treatment and monitoring can be even more stringent. Reuse is essentially a way to keep water circulating locally, instead of using it once and losing it. Water reuse can be especially helpful in arid regions because it creates a more reliable supply that does not depend entirely on rainfall timing. Cities that reuse water can reduce how much they withdraw from rivers or aquifers. Over time, reuse can also make water systems more resilient during drought. It is one of several strategies, along with conservation and efficiency, that helps match limited supplies to growing demand. Stormwater management practices, like rain gardens and permeable pavements, aim to reduce polluted runoff and allow more water to soak into the ground. Instead of quickly sending rain into drains, these designs slow water down so it can infiltrate and be filtered by soil. This reduces flooding risk and can improve water quality by trapping sediments and nutrients. It also supports groundwater recharge in areas that would otherwise shed most rainfall immediately. Permeable surfaces allow water to infiltrate through small gaps and pores rather than running off as a fast sheet. This can reduce the sudden surge of flow that overwhelms storm drains during heavy rain. It also helps water return to soils, where it can feed plants and recharge groundwater. Permeable designs are a quiet way to make urban areas behave a little more like natural landscapes during storms. Green roofs can retain rainfall and slow runoff because the plants and soil-like layers temporarily store water. Some of that stored water later evaporates or is taken up by plants, and the rest drains more slowly than it would from a hard roof. This can reduce flood peaks and help moderate building temperatures as well. The water behavior here is small scale, but across a city it can add up to meaningful changes. Dams store water, generate hydropower, and control floods, but they also change how rivers behave by altering flow patterns and trapping sediment. When a river is interrupted, seasonal high flows can be reduced and low flows can be increased, reshaping habitats downstream. Sediment that once traveled to deltas and beaches can settle in reservoirs instead. This shows how controlling water in one place often changes landscapes and ecosystems elsewhere. Reservoirs can trap sediment that would normally nourish downstream deltas and beaches, which can lead to erosion over time. Deltas rely on a steady supply of sediment to maintain their elevation against sinking land and rising seas. If sediment is held back, the delta may shrink or become more vulnerable to storm surges. This is a direct result of how moving water carries particles and how slowing water encourages those particles to settle. Hydropower converts the energy of stored or flowing water into electricity by using turbines that spin as water passes through. The energy comes from gravity and elevation differences, water falling from higher to lower levels. Hydropower can provide steady electricity with low direct emissions during operation. Its practicality depends on geography, water availability, and how river ecosystems are managed around the infrastructure. Pumped storage hydropower moves water uphill when electricity is abundant, and then releases it through turbines when demand is high, acting like a large energy storage system. It is essentially a water-based battery. Energy goes in to lift the water, and energy comes back out when the water flows down again. This can help stabilize electric grids, especially when power supply fluctuates. The system relies on water's mass and gravity rather than chemical storage. Canals and aqueducts move water across long distances, often from wetter regions to drier ones, using carefully controlled gradients, tunnels, and pumps. Because water is heavy, moving it requires major engineering and ongoing maintenance. These systems can support agriculture and cities, but they also create dependencies between regions. A change in supply or climate upstream can affect faraway users downstream. Water rights and allocation systems differ widely by region, and they shape who can use water, when, and in what quantities. Some systems prioritize historical use, some prioritize ecological needs, and others use market-like mechanisms. Because water availability changes with seasons and drought, allocation rules can strongly influence resilience. In practice, water management is as much about governance as it is about hydrology. In many cities, water loss from leaks can be a major efficiency issue because treated water escapes before reaching customers. That lost water represents not only the water itself, but also the energy and chemicals used to treat it. Leak reduction can be one of the fastest ways to increase effective supply without finding new sources. It also helps maintain pressure, which supports both reliability and water quality. Smart meters can detect unusual use patterns that may indicate leaks, such as continuous water flow at times when a home should be quiet. By spotting these patterns early, utilities and residents can repair problems before they become large losses. Smart meters can also help people understand their own water habits, making conservation more practical. The underlying idea is simple. Measuring water use more precisely helps manage it better. Evaporation from open reservoirs can be significant in hot, dry climates because warm air and low humidity encourage rapid water loss from the surface. Wind can further increase evaporation by removing humid air right above the water. Over time, this can reduce stored water and change how operators plan releases. It's a reminder that stored water is not fully sealed away from the atmosphere. Some reservoirs use floating covers or shade structures to reduce evaporation by limiting direct sunlight and reducing wind effects at the surface. By lowering surface heating and air-water contact, these designs can slow the escape of water vapor. They can also reduce algae growth by limiting light. This is an engineering response to a basic physical process. Evaporation increases with energy and exposure. Groundwater banking stores surplus water underground for later use, using the ground as a natural storage space. Instead of letting extra water run off during wet periods, it can be directed into recharge basins or injection wells. Underground storage can reduce evaporation losses compared with surface reservoirs. It can also help stabilize groundwater levels and provide a buffer during drought. Managed aquifer recharge can use infiltration basins, injection wells, or riverbank filtration to increase groundwater supplies. The goal is to intentionally move water into the ground in a controlled way, rather than relying only on natural infiltration. Infiltration basins let water soak through soils that can remove some particles and microbes. Injection wells place water directly into deeper layers, which requires careful treatment and monitoring. Riverbank filtration naturally filters river water as it moves through sediments toward wells near a river. As water travels through sand and gravel, many particles and some microbes can be reduced, and certain chemicals can be transformed by natural biological processes. This can improve raw water quality before it reaches a treatment plant. It is a quiet partnership between geology and engineered water supply. A water footprint estimates how much fresh water is used directly and indirectly to produce goods and services. Direct use might be the water someone drinks or uses at home, but indirect use includes water used to grow food, manufacture materials, and generate energy. Two similar products can have very different footprints depending on how and where they are produced. This concept helps connect everyday choices to distant water resources. Virtual water refers to the water embedded in products that are traded internationally, meaning water is effectively moved around the world through commerce. When a country imports water-intensive crops, it is also importing the water used to grow them. This can relieve pressure on local water supplies in dry regions. It also means global markets are tied to global water availability in ways that are not always obvious. Agriculture is often a large share of freshwater withdrawals, because crops require water over long growing seasons, and irrigation can be needed when rainfall is unreliable. Water is used not only for plant growth, but also to manage soil temperature, salinity, and nutrient transport in fields. Efficiency varies widely depending on crop type, climate, and irrigation method. Because farming uses so much water, small improvements in efficiency can lead to large total savings. Drip irrigation delivers water near plant roots through tubes and emitters, reducing evaporation and runoff compared with many surface methods. By placing water where plants can use it most effectively, drip systems can lower waste and reduce weed growth between rows. They can also be paired with precise timing to match plant needs. The trade-off is that drip systems require maintenance to prevent clogging and ensure even distribution. Sprinkler systems can be efficient when well managed, but wind and heat can increase losses because small droplets can drift away or evaporate before reaching the soil. The timing of irrigation matters. Applying water during cooler, calmer times can reduce evaporation. Nozzle selection and pressure control also affect droplet size and distribution. Good design turns sprinklers from a broad spray into a more targeted delivery system. Soil type affects irrigation needs because sandy soils drain quickly and hold less water, while clay soils hold water longer but can drain slowly and become waterlogged. In sandy soil, frequent small watering may work better because water moves downward fast. In clay, slower application can prevent runoff and help water penetrate evenly. Understanding soil is essentially understanding how water moves through tiny pore spaces. Mulching reduces evaporation from soil by shading the surface and limiting wind exposure, helping moisture stay available to plants longer. Mulch can be organic, like straw or wood chips, or inorganic, like certain films. By slowing water loss, mulching can reduce irrigation demand and stabilize soil temperature. It is a simple technique that works because evaporation depends strongly on surface energy and exposure. Watersheds are areas where all precipitation drains toward a common outlet, such as a stream junction, a river, or the sea. What happens upstream, land clearing, farming, urban growth can affect water quality and flow downstream. Because water collects and travels, a watershed connects many communities and ecosystems. Thinking in watersheds helps people see rivers as integrated systems rather than isolated segments. Watershed boundaries are typically defined by ridgelines and high ground that separate where water will flow during rain. On one side of a ridge, water drains into one river system. On the other side, it drains into a different one. These boundaries can be mapped using topography and are used in planning and environmental management. They're a clear example of how landscape shape guides water movement. Urbanization often increases runoff because impervious surfaces like roads and roofs prevent infiltration. Instead of soaking into soil, rainwater runs quickly into gutters and drains, creating sudden pulses of flow in streams. This can increase flood risk and reduce groundwater recharge. It can also carry pollutants from streets into waterways, making water quality management more challenging. Streams in urban areas can become flashier, meaning water levels rise and fall quickly during storms. Rapid runoff leads to high peak flows that can erode channels and damage habitats, followed by low flows when the storm passes because less water infiltrated to support base flow. This altered rhythm can stress aquatic life adapted to steadier patterns. It reflects how changing the land surface changes the timing and energy of water movement. River restoration can include reconnecting floodplains, adding habitat structures, or removing barriers to improve ecosystem health. Reconnecting a floodplain gives water room to spread during high flow, reducing channel erosion and supporting wetlands. Habitat structures can create pools and shelter for fish. Removing or modifying barriers can restore natural migration pathways and improve how water and sediment move. Fish ladders and bypass channels can help some species move past dams, though their effectiveness depends on design and on the swimming abilities and behavior of each species. A structure that works for one fish may not work for another. Flow speed, turbulence, and attraction flow all matter in guiding fish to the passage. These designs try to blend engineering with biology, so the river remains more connected. Environmental flows aim to preserve enough water in rivers to support ecosystems, while also meeting human needs. Many species depend on seasonal flow patterns, higher flows for spawning or floodplain access, lower flows for certain habitats. If a river is held too constant or too depleted, these ecological signals can disappear. Environmental flow planning tries to keep a river's living rhythm intact. Relative humidity is a measure of how close the air is to being full of water vapor at a given temperature. Warm air can hold much more water vapor than cold air, so the same amount of moisture can feel very different depending on temperature. That's why relative humidity can drop in the afternoon as the air warms, even if no moisture actually left the air. It's a simple percentage, but it explains a lot about why air feels dry, sticky, or ready to form clouds. Specific humidity is different from relative humidity because it describes the actual amount of water vapor in the air, not how close the air is to saturation. You can think of it as the true water vapor content, which makes it useful for comparing different air masses, even when their temperatures are different. This is why meteorologists often look at specific humidity when tracking moisture moving in from oceans or building up ahead of storms. It helps separate how much water is there from how easily it will condense. Dew point is the temperature at which air becomes saturated and water vapor begins to condense into liquid water. A higher dew point means the air contains more moisture, while a lower dew point means the air is drier. Because dew point is tied directly to moisture content, it often feels like a more straightforward way to describe muggy air than relative humidity. When nighttime temperatures fall to the dew point, dew forms quietly on surfaces. In very cold conditions, tiny ice crystals can stay suspended in the air and create what is often called ice fog. Instead of droplets of liquid water, the air holds fine crystals that can sparkle under light and reduce visibility. This happens when the air is extremely cold and has enough moisture to deposit directly into ice. It's one more way water can shift between phases in the atmosphere without much fanfare. Water in the atmosphere often needs tiny particles to help it condense into droplets, and those particles are called condensation nuclei. Without these nuclei, water vapor would have a harder time forming stable droplets, and cloud formation would be less efficient. Dust, sea salt, smoke, and other aerosols can all serve this role. In a quiet way, the presence of particles helps decide when and where clouds appear. Sea spray aerosols are tiny salty particles thrown into the air when waves break and bubbles burst at the ocean surface. These particles can help seed clouds by giving water vapor a surface to condense onto. They also influence how sunlight is scattered and reflected, which can affect how bright clouds look from above. It's a subtle bridge between ocean surface action and the atmosphere overhead. Water in rivers tends to gain oxygen more easily where the flow is turbulent, such as in riffles, rapids, and small waterfalls. Turbulence increases the contact between water and air, making it easier for oxygen to dissolve into the water. This can create healthier conditions for many fish and insects, especially in warm seasons when oxygen is harder to hold. Even small variations in stream shape can change oxygen levels. Waterfalls and rapids often appear where rock layers differ in hardness, causing uneven erosion over time. Softer rock wears away faster, leaving harder rock as a ledge that water drops over. The falling water then continues to erode the base, sometimes shifting the waterfall's position slowly upstream. What looks like a fixed feature is often a landscape in slow motion. Water can store heat so well that it's commonly used in thermal energy storage systems, where large tanks hold warm or hot water for later use. This works because water can absorb a lot of energy without heating up extremely fast, so it can act like a stable heat bank. Buildings can collect heat when energy is cheaper, or when solar energy is abundant, then use that stored heat later. The steadiness of water temperature makes the system predictable. Solar thermal systems often rely on water or water-based fluids to carry heat from collectors to where it will be stored or used. Water warms in the collector, flows through pipes, and transfers its heat through a heat exchanger or directly into a storage tank. In cold climates, systems may use additives to prevent freezing, but the basic idea remains the same. Water is a convenient, effective carrier of heat. It turns sunlight into a usable thermal resource. Hydronic heating uses circulating hot water to warm rooms through radiators or tubing in floors and walls. Because water carries heat efficiently, it can deliver warmth evenly and quietly across a building. After releasing heat, the cooler water returns to be reheated, creating a continuous loop. Many people find the warmth from hydronic systems gentle and steady because it avoids the rapid temperature swings of some forced air systems. Cooling towers use evaporation as a powerful cooling method, taking advantage of water's large heat of vaporization. When a small portion of water evaporates, it carries away a large amount of heat, cooling the remaining water. That cooled water can then be reused to remove heat from industrial processes or building systems. It's a controlled, engineered version of the same cooling principle, that makes evaporation from skin feel cool. Water can be used as a radiation shield in some settings because it can slow down and absorb certain kinds of radiation. Its density and its hydrogen atoms make it particularly effective at reducing the energy of neutrons. In nuclear facilities, deep pools of water can both cool equipment and provide shielding at the same time. It's a practical example of how basic physical properties translate into safety. When water is used to fight fires, its biggest strength is how much heat it can absorb before it changes phase into steam. By cooling burning materials, water can lower temperatures below what's needed to sustain combustion. As water turns to steam, it expands dramatically, which can also help reduce oxygen near flames in certain conditions. Fire suppression is at its core a careful use of water's thermodynamics. Water mist systems can suppress fires using very fine droplets that absorb heat quickly and reduce radiant heat. Tiny droplets have a large surface area compared with their volume, so they evaporate efficiently and cool hot gases rapidly. This can help slow flame spread and make conditions less supportive of burning. Mist can be especially useful in certain enclosed or sensitive environments where rapid cooling is valuable. At the surface of a very hot pan, the Leidenfrost effect can make a droplet of water glide on a thin cushion of its own vapor. The bottom of the droplet flashes into vapor instantly, and that vapor layer insulates the rest of the droplet from direct contact. Because of that insulation, the droplet can survive longer than expected and move smoothly across the surface. It's a vivid demonstration of how phase change can create a protective barrier. When water freezes inside a confined pipe, it can cause bursting because ice takes up more volume than liquid water. As ice forms, it expands and pushes outward, creating intense pressure if there is no space to expand. The pipe material may crack or split under that pressure. This is why winterizing plumbing involves preventing water from freezing or giving it room to expand safely. Adding antifreeze or salts lowers water's freezing point, which helps prevent freezing in certain systems. These dissolved substances interfere with the formation of an ordered ice crystal structure, so the liquid can stay unfrozen at lower temperatures. This principle is used in car cooling systems and sometimes in ice management on roads. It's another everyday effect of how dissolved particles change phase behavior. Sea level can change when water warms because warmer water expands slightly, a process known as thermal expansion. Even a small expansion per unit volume becomes significant when applied to the entire ocean. Sea level also rises when land-based ice melts and adds water to the ocean. These are quiet, physical processes that accumulate over large scales. Icebergs come from glacial ice that breaks off into the sea, and only a small fraction is visible above the surface because ice floats with most of its volume submerged. The visible tip can be impressive, but the larger mass lies underwater, shaped by melting and currents. As icebergs drift, they can deliver fresh water into the ocean and influence local salinity. They also carry minerals and sediments embedded in ice from their original land sources. Glacial meltwater can carry extremely fine sediment, often called rock flour, that stays suspended and makes lakes look milky or turquoise. The particles are so small that they scatter light in distinctive ways. This coloring can be most striking in glacier-fed lakes during warm seasons. It's a gentle visual reminder that water can transport the smallest fragments of landscapes. Under glaciers, meltwater can carve channels and tunnels that affect how a glacier slides and fractures. Water at the base can act like a lubricant, reducing friction between ice and rock. Changes in these hidden water pathways can alter glacier speed, sometimes causing short-term accelerations. Even deep beneath ice, liquid water can shape the motion of a massive frozen body. In many ocean regions, the surface mixed layer forms where winds and waves stir the upper water and blend temperature and salinity into a more uniform layer. This layer is often where sunlight penetrates and where much marine life is concentrated. The depth of the mixed layer changes with seasons, storms, and heating. It acts like the ocean's active skin, responding quickly to the atmosphere. A thermocline is a zone in the ocean where temperature changes rapidly with depth, separating warmer surface water from colder deep water. This boundary can limit mixing, which affects where nutrients and oxygen move. Many organisms position themselves near thermoclines because conditions can change sharply across a small vertical distance. It's one of the reasons the ocean can feel layered and structured rather than uniform. A halocline is a zone where salinity changes rapidly with depth, which can also create strong density layering. In estuaries or enclosed seas, fresher water can sit above saltier water, creating a stable boundary that resists mixing. This layering influences how oxygen reaches deeper zones and how organisms distribute themselves. Water's salt content becomes an organizing force in the vertical structure of the sea. Oxygen minimum zones can form where oxygen is consumed faster than it is replenished, often in regions with strong biological activity and limited mixing. When organisms die and decompose, microbes use oxygen while breaking down organic matter. If circulation does not bring in enough oxygenated water, levels can drop. These zones shape marine habitats by creating areas where only certain species can tolerate low oxygen. Upwelling happens when winds or currents bring deep, nutrient-rich water toward the surface. Those nutrients can fuel phytoplankton growth, which supports rich food webs of fish and marine mammals. Upwelling regions are often among the most productive fisheries in the world. It is a powerful example of how vertical water movement can influence life at the surface. Downwelling pushes surface water downward, carrying oxygen and surface properties into deeper layers. This helps ventilate parts of the ocean and supports deep water ecosystems with oxygen supply. It also helps move heat and dissolved gases downward. While upwelling is often more visible through productivity, downwelling is equally important for balance and circulation. Estuaries mix freshwater and seawater, creating gradients that change from river-like conditions to ocean-like conditions over short distances. These gradients affect which species can live where, because salinity tolerance varies widely. Estuaries also tend to be rich in nutrients and sheltered from strong waves, making them important nurseries for many fish and invertebrates. They are transitional zones where water chemistry and biology shift gently and continuously. Seagrass meadows are underwater flowering plants that stabilize sediments and provide habitat for many species. They slow water flow near the bottom, which reduces erosion and helps particles settle. Seagrasses also store carbon in their tissues and in the sediments they trap. In clear, shallow waters, they can create calm, structured environments that support diverse life. Mangroves tolerate brackish water and can protect shorelines by trapping sediment and reducing wave energy. Their tangled roots slow water, allowing mud and sand to settle and build land. Mangroves also provide nurseries for fish and shelter for many birds and invertebrates. They show how plant structure can shape water movement and coastline stability. Plankton includes tiny drifting organisms, and phytoplankton photosynthesize, forming the base of many aquatic food webs. When conditions are right, enough light, suitable temperature, and available nutrients, phytoplankton can multiply quickly. They feed zooplankton, which feed fish, and so on up the chain. Much of the ocean's life ultimately depends on these small floating producers. Many fish sense water movement with the lateral line system, which detects subtle pressure changes and vibrations. This allows fish to school smoothly, avoid obstacles, and detect predators or prey, even in low light. The lateral line turns water into an information-rich medium, where movement carries signals. It's a quiet sensory partnership between biology and fluid physics. Buoyancy in water lets organisms save energy, but many animals still need ways to control their depth. Some fish use swim bladders to adjust internal gas volume, while others rely on oils, body composition, or swimming motion. Small changes in buoyancy can determine whether an animal drifts upward, sinks, or stays level. Water's density becomes the background against which these fine adjustments matter. Freshwater fish constantly manage osmosis because the water around them is less salty than their body fluids. Water tends to move into their bodies, and salts tend to move out, so they excrete dilute urine and actively absorb salts through their gills. This regulation keeps internal chemistry stable, so muscles and nerves function properly. It's a steady balancing act that happens quietly as the fish swims. Marine fish face the opposite challenge because seawater is saltier than their body fluids. They tend to lose water to the environment and gain salts, so many marine fish drink seawater and then excrete excess salts through specialized cells in their gills. They also produce smaller volumes of more concentrated urine. Their survival depends on managing water and salt as a continuous exchange. Some species, like salmon, can transition between freshwater and seawater by changing how their bodies regulate salts. Before migrating, they remodel gill cells and adjust hormone systems that control ion transport. This transformation allows them to handle very different osmotic conditions without losing balance. It's one of the most impressive examples of physiological flexibility tied directly to water chemistry. In lakes, summer stratification can limit oxygen replenishment to deep waters because warm surface water stays above colder deep water and mixing is reduced. If decomposition in deep water consumes oxygen, levels can fall over time. When autumn cooling arrives and surface water becomes denser, mixing can return and restore oxygen. This seasonal pattern shows how temperature layering can quietly control breathability underwater. In winter, some lakes develop a stable layering under ice, with the coldest water near the top and slightly warmer water near the bottom. Because fresh water is densest around 4°C, water near that temperature can settle below the colder surface layer. This helps keep deeper water liquid even when the surface is frozen. It creates a calm winter structure that can protect many organisms until spring. Riverbank filtration can naturally improve water quality because river water moves through sediments before reaching wells. As water travels through sand and gravel, particles can be trapped and some microbes can be reduced. Chemical conditions in the sediments can also transform certain compounds. This process is not a complete substitute for treatment, but it can act as a helpful first step shaped by geology. Groundwater and surface water often exchange with each other. So a river can either gain water from the surrounding aquifer or lose water into it. If the water table is higher than the river, groundwater seeps into the channel and supports flow during dry times. If the water table is lower, river water can leak into the ground and help recharge groundwater. The direction can change seasonally, making rivers and aquifers a connected system. Some springs are thermal because groundwater is heated as it travels deep enough to pick up geothermal warmth. As it rises back to the surface, it can emerge noticeably warmer than surrounding air and streams. The mineral content can also differ because warm water dissolves certain minerals more effectively. Thermal springs are a gentle surface hint of heat below ground. Geysers require a rare combination of heat, water supply, and underground plumbing that allows pressure to build and release in cycles. Water seeps down, is heated, and can become superheated under pressure without boiling. When boiling finally begins, steam expands and pushes water upward, triggering an eruption. Afterward, the system refills and the cycle can repeat, sometimes with surprisingly regular timing. Water can be stored in minerals as water of crystallization, where water molecules are part of the mineral's structure. When such minerals are heated, they can release that water, changing the mineral's properties and sometimes its appearance. This is important in geology and in industrial processes where heating drives chemical changes. It's a reminder that water can exist not only as free liquid or ice, but also as part of solid materials. Even though Earth's total water amount is relatively stable over human timescales, the way water is stored can shift more in the ocean, less in glaciers, more in the air, less in soil moisture. Those shifts can reshape ecosystems, influence weather, and change how reliable rivers and aquifers feel. In that sense, water's calm presence is also dynamic, always moving between reservoirs. And as you let your attention settle, it can be enough to remember that so much of Earth's steady rhythm, clouds, rivers, and the quiet turning of seasons, depends on this simple molecule finding its way again and again